Hello everyone, this is Ling-Jyh from Academia Sinica, Taiwan. Today, the topic of my talk is the application of the Internet of Things in air quality monitoring. I will use our project called AirBox as an example and discuss how the Internet of Things can be used for air quality monitoring, as well as how we make sense of AirBox data to address problems that most people are concerned about. Before we start, I think we should give a brief introduction to the Internet of Things. The Internet of Things is composed of multiple sensing devices, which are connected to the Internet through various methods, such as Wi-Fi, Bluetooth, 3G, 4G, and 5G. Each device measures its use and contributes to the backend database at a predetermined rate. The backend server receives the data stream from all the sensors deployed in the field, which will soon become a large-scale time series or spatial temporal data stream, which can be visualized, processed, and analyzed to provide insight into the overall scenario. In addition, using the collected big data, we can also apply all kinds of AI and machine learning techniques to even deepen our investigation and figure out the knowledge, wisdom from the data. Today, you may have heard many so-called smart blah 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 applications, such as smart city, smart healthcare, smart home, and so on and so forth. And these smart blah 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 are all built based on the Internet of Things to collect data, process information, and generate knowledge, wisdom from the data. This is why we call it smart. In this presentation, I will use our AirBox project to show how the Internet of Things can help air quality monitoring and how much we have achieved using the data collected from the AirBox deployments in the past few years. Let me show you some quick facts before and after our deployment in the next slide. As you can see, before we started the AirBox project, if Taiwanese were interested in air quality data, they could only rely on 77 professional EPA stations, which will give you the measurement results every hour. However, today, if you want to know the air quality in the area around you, we have deployed more than 12,000 devices, and each device returns a measurement result every 5 minutes. It is conceivable that under very intensive deployment and frequent sampling, we have greatly reduced the spatial and temporal granularity of air quality monitoring, so we can answer people's inquiries about air quality in their microenvironments. Of course, since our system uses low-cost air quality sensors, it may lose some accuracy if compared to professional EPA stations. However, it has also proven to be a good research problem for big data analysis and artificial intelligence, and I will show you how we have overcome these problems in the following slides. Now, let me take a few minutes to take a quick look at the development process of the project. Our project has 3 components. The first one is to enable this technology and make low-cost air quality sensing possible. We started this project from scratch 7 years ago and gradually learned how to assemble sensors, how to make PCB boards, how to use Wi-Fi, Bluetooth, 4G to send sensor data to the outside world, and how to use 3D printing to design the housing. We also evaluate various low-cost air sensors for professional equipment and find good quality sensors that can be used in our projects. Fortunately, we found a low-cost PM2.5 sensor with good performance. The second component of the project is to empower people to use this technology and copy our work to make their own work. We decided to use open hardware which is commercially off the shelf and easy to be used and even modified when needed. We also published our source codes on GitHub so people can track and even contribute our codes. Finally, we decided to publish all the collected data in an open data format and in real time. There are several reasons for this. Number one, we hope to reduce technical boundaries so everyone can easily join us. Number two, we want to build trust between the participants and our team because everything is open and public. Number three, we hope to recruit more diverse people. For example, people can join our project by making devices to contribute data, fixing our codes, or contributing new features, or just using our data for their research or developing new applications. In addition, we have designed multiple visualization tools to help people understand the data collected from the AirBox project. We found it very useful, especially for using our system to promote citizen science. The third component is to engage people to participate, collaborate, and contribute. The project was originally an academic research project, and then we worked with a local community called Location-Aware Sensing System to recruit people from different backgrounds. Then, we were fortunate to receive a 4-year government grant to deploy AirBox devices in every K-12 school in Taiwan. The focus of the project has also changed over time. At the beginning, we focused on sensor deployment, and then turned to data analysis after collecting a large amount of data from the deployment. Now, we focus on interdisciplinary cooperation to solve real-world problems. Therefore, the project has established a very active and healthy ecosystem involving academia, communities, industries, governments, educational schools, and teachers. These 5 components voluntarily contribute to the system and help each other to keep the ecosystem circulating. To date, the project has deployed more than 12,000 devices in 59 countries. We have established close collaboration with major research universities in Taiwan and have close collaboration with other major low-cost air sensing projects around the world, such as the Array of Things project in Chicago, the AQNU project in Utah, the Smart AQNet project in Germany, the City Air project in Russia, the Dust Boy project in Thailand, and Purple Air in the United States. In addition to deploying and setting up the network, we also put forward some research results. For example, we propose a comprehensive evaluation that compares our equipment with professional equipment and evaluates the consistency performance between AirBox devices. Of course, the results are very encouraging and promising. In order to handle thousands of real-time IoT data streams, we have also developed a powerful backend architecture that can monitor a large number of devices, correctly store the data in different databases, and publish the measurement results in JSON or CSV format in real time. Using the collected data, we implemented an inverse distance weighting algorithm to interpolate the air quality between AirBox devices. We took a snapshot of the visualization results every 20 minutes and made animations to visualize how the air quality distribution changes over time. For example, on the right-hand side, the animation shows the long-distance transmission of dust and pollutants from north side of Taiwan to the south side. The animation was produced in January 2017. This is the first time in history that we can crowdsource low-cost air sensor data and visualize such pollution events with such granularity. In addition, the second animation was shot during a cultural event in central Taiwan. During the event, people burnt incense and gold money almost at the same time to celebrate the birthday of the most important god. As we can see in the animation, the air quality in central Taiwan turned purple, indicating the PM2.5 concentration was very high, and turned back to orange color after the events. It turns out that it's the perfect material for environmental education because human behavior may affect our environments, especially when a large group of people do things together. We also considered the data quality issues in our system and implemented an anomaly detection framework called ADF to use spatial temporal data analysis to detect pollution events and abnormal devices. This work is actually very challenging because several reasons. One, the accuracy of the device is not as good as that of the EPS station, so our solution must tolerate slight errors in the data stream. Number two, the device is not time synchronized, so our solution must implement the concept of time window slice in our data analysis. Number three, the solution must distinguish between outliers and air quality events, even if they have similar patterns in the time series data stream. And number four, the solution must be simple and fast in order to be able to support online calculations and publish results in almost real time for further applications. The idea of our method is to detect two types of anomalies from the sensor data streams. The first type is called spatial anomaly, which means that the AirBox device behaves differently from other nearby devices. The second type is called time anomaly. That means the measurement data of AirBox changes drastically in a very short limit time. Based on the frequency of these two types of anomalies, we can calculate the critical values of each AirBox device. And based on the appearance patterns of these two types of anomalies, we can infer the cause of this anomaly, such as the device is located indoors, there is the fixed source of emissions near the device, or a burning event is occurring near the equipment. As you can see in the figure, we have successfully implemented our anomaly detection framework and released our analysis results to the public almost in real time. And the results of our analysis were imported by Taiwan's hacker community, Zero Government, and they create a very beautiful data visualization on their website. In their design, they provide different icons to represent AirBox devices with different attributes so that people can easily understand that the devices when viewing the PM2.5 map website. We also applied machine learning to the AirBox dataset and contribute on PM2.5 data prediction research to predict short-term PM2.5 concentrations. Here, I mean prediction the PM2.5 concentration in the next 1 to 5 hours. Compared with the traditional data prediction problem, short-term PM2.5 prediction is very challenging because you must train the model, update the model frequently, and give the prediction results in a very timely manner. For example, you may only have 1 minute to complete the entire work and generate prediction results for 10,000 AirBox devices. To solve this problem, we consider the solutions in 2 dimensions. One is accuracy, which means we want to have a solution that can provide us with as accurate results as possible. To this end, we have applied modern machine learning techniques such as neural networks or even deep learning to achieve high precision predictions. But the training phase may take too much time to make this solution feasible for our purposes. And the other dimension is scalability, which means we want to generate predictions in a limited time frame for as many AirBox devices as possible. For example, we can model the prediction problem as a matrix optimization problem to find the transition matrix between two consecutive time slots. Then we can apply the transition matrix to generate data prediction results for the next time slot very quickly, even though the error is also becoming larger and accumulated. Obviously, these two dimensions are contradictory, and there must be something in the middle between the two extremes. So, we studied different clustering techniques to identify different AirBox groups with similar spatial-temporal behavior and trained models for each group. And then, we applied this model to other AirBox devices in the same group to generate prediction results. As you can see on the figures, the calculation time has been significantly reduced using our method, while the accuracy performance is still acceptable. This is just an attempt to strike a good balance between accuracy and scalability, and more research on this topic is still in progress, and we hope that there will be new results very soon. Next, once we obtained the real-time PM2.5 data from intensive deployment and short-term forecast data from forecasting services, we developed a new navigation service called Clean Air Routing to provide people with minimal PM2.5 exposures routes in the city. By talking about minimal PM2.5 exposure, we are talking about the total amount of PM2.5 accumulated over time during your movement. As you can see, if you want to move from the red dot on the right to another red dot on the left, Google's shortest path algorithm will provide you with a great path. However, our clean air routing algorithm will provide you with a blue route that will turn to the riverside and then to the downtown city, where there are very few vehicles at that time. The total PM2.5 exposure score dropped from 75 to 59, but the travel time was about 30 minutes longer than the shortest one. The clean air routing application is just an attempt to design an innovative application based on a low-cost air sensor IoT system. By providing more fine-grained spatial temporal measurement data, we believe that more and more new applications will be created, and these applications will enable data-informed decision-making in the long run. These applications are very important to IoT systems, not only because they would not be possible without IoT deployment, but also because they can understand IoT systems and make the IoT visible to the public. Recently, we also work with cross-disciplinary experts to address classic problems in other fields. For instance, in spatial statistics and public health, it is essential to predict ground-level PM2.5 concentrations using nearby air quality station data, and the results can benefit health impact assessment of cohorts with PM2.5 exposures. Traditionally, the prediction considers EPA station data, meteorological data, and spatial attributes. On top of the state-of-the-art, we consider data from the AirBox network and adjust the interpolation parameters based on AirBox data analysis. The results are very promising, as the R-squared value is more stable at 0.87, and the RMC is reduced to 4.1 microgram per cubic meters. The result of this study may benefit many ongoing public health studies in finding the correlation between PM2.5 exposures and different diseases, and we are still working on improving prediction accuracy of the work and looking for collaboration too. Currently, we have also established a dynamic calibration framework in cooperation with Taiwan's EPA to calibrate low-cost AirBox data. First, we selected 31 EPA sites as reference points, and each site deployed 2 AirBox devices to conduct a parallel comparison testbed. Then, for each reference site, we considered more than 200 model configurations and selected the one with the best accuracy performance as the reference site's calibration model for that day. Then, for each AirBox device in Taiwan, we find the reference site closest to the device and apply its calibration model to the AirBox. We understand that there may be some models that can provide even better accuracy performance in calibration, but given our limited knowledge and computing resources, this is the best effort we can achieve so far. Based on the calibration data, we also give activity suggestions when we release the measurement results to the public. In addition, we also publish the model on the website in binary form, as well as detailed parameter configuration, so that people can reproduce the results. We believe that keeping everything open during the calibration process is very important, because this is the best way to build and maintain public trust. This is also important for the research community, because we need to ensure that the results can be reproduced in the future. So far, I have shown you some research results of AirBox. Next, I want to share with you some interesting findings that we learned from experiments when promoting citizen science and environmental education. For example, we can use the mask of different materials to package our device and understand which mask material can best prevent PM2.5 exposures. We can also use our device to measure the PM2.5 concentration before and after turning on the air purifier to compare the performance of different models of air purifiers by crowdsourcing tests to the community. We also installed AirBox in my vehicles and conduct a very simple experiments to study the air quality of the interior recirculation and exterior air. This AirBox is the special version made by my team. It has PM2.5 and CO2 sensors. When I got in the car, the PM2.5 and CO2 readings were about the same as the outdoor conditions, and I started using the internal air recirculation drive. As you can see on the slide, the PM2.5 curve slowly drops because the air inlet is equipped with the filter, and the air is getting cleaner after being recirculated. However, you will find that the CO2 curve grows very fast, reaching 2000 ppm after 20 minutes. We know that after a period of such high concentrations, people may feel sleepy and inattentive, which can be dangerous when driving at high speed. Then I switched the air conditioner to outside air mode, and the CO2 concentration quickly dropped to less than 700 ppm in just 3 minutes, which was acceptable. The PM2.5 level also increased to 32 microgram per cubic meters, which is approximately equal to the outdoor PM2.5 level. It turns out very interesting that when driving on the road, we need to switch back and forth between air recirculation and fresh air mode, so that we can achieve a good balance between energy saving and good air quality in the car. So, what's the next step for the AirBox project? There are still many open challenges ahead. For example, in terms of equipment hardware, we hope to integrate additional sensors into the system, such as CO2, TVOC, sound, and light sensors. We hope to study energy harvesting on AirBox and make the system self-sustaining in the future. We hope to strengthen the security design of our system and gradually offload some data analysis and machine learning tasks to edge IoT devices for edge computing. In addition, in terms of big data, we hope to deepen our research on multi-resource data fusion and use cyber-physical social data as a whole to understand the interaction between the environment, the cyber world, and the social media. We hope to cooperate with environmental experts and apply artificial intelligence technology to strengthen model-based simulation research. We hope to combine AI technology and GIS applications to form GeoAI and embed this intelligence into future database systems. Finally, in terms of applications, we hope to shift the focus to indoor scenarios and promote more interdisciplinary research, collaborations, and international cooperation. We hope that all these efforts will help to promote data-informed decision-making in the near future. Okay, let me end this conversation. In this talk, I introduced an application of the Internet of Things in air quality monitoring. The project is called AirBox, and there are several lessons that we learned from the project. Number one, open is the key to making things possible and making the overall solution scalable. Number two, the power of the Internet of Things is to make sense of data. Number three, there are many challenges and research issues in the future. I encourage you to think about the must-have problems rather than nice-to-have problems, because this is the only way to make your system meaningful in the real world. There are still many unsolved challenges, and I look forward to working with you in the near future. This is the end of my talk. Thank you very much for your attention.